Okay, so this next one, I've got an integral 3 to 5, ln of x cubed dx. That's not a nice little u substitution integral, unfortunately. But let's approximate it using a power series here. And let's use 3 non-zero terms. All right, so in our previous example, we just used a Maclaurin series. Do you think it'd be appropriate here to use a Maclaurin series? No, why not? Yeah, 3 to 5, that's a little far off from 0. So we're not going to use the Maclaurin series since it's not, I mean, there is an ln Maclaurin series, but it's not applicable here because it's not centered at 0. So we'll just use the Taylor series. Like I said, 3 non-zero terms. That'll probably be the first 3 terms here. So we're going to approximate this with the Taylor series first 3 terms. So the Taylor series, we start off with f of a plus f prime of a over 1 factorial x minus a to the 1 plus f double prime, the second derivative of a over 2 factorial times x minus a squared. That'll probably be non-zero terms. I guess we can make sure about that. But now, here we have a choice. A is our center. And so we can center it where we want to. Well, 3 to 5, center at 4. Yeah, since that's right smack dab in our limits, let's center it up at a equals 4. So we do f of 4, f prime of 4, and then f double prime of 4. Those will probably be, unless they're non-zero. Oops. So let's do that. Let a equal 4. Seems to be a good center for us on that one. All right, so we've got our f of x is this ln x cubed. So the first derivative would be 1 over x cubed, but by chain rule times 3x squared, hey, that's just 3 over x, isn't it? And then for derivative purposes, it's 3x negative 1, because the second derivative then would be negative 3x minus 2. And evaluate those at 4, so that would be ln of 4 cubes, that would be ln of 64. F prime of 4 would be 3 over 4, wouldn't it? 3/4. 1 factorial is 1, I don't know why I keep writing that. But, then f double prime at 4, so that would be negative 3 over 4 squared, 16. So it'd be negative 3/16. Divided by 2 factorial, that'd be 2. Yeah, so those give me 3 non-zero terms. Oh, and we are forgot one very important little thing here. It's an integral. So I'm doing the integrals 3 to 5 of these, not just evaluating them. I'm doing the integral of them 3 to 5. Yeah, so I mean, you can go ahead and multiply those out, but probably the easiest thing here is just going to be integrate it right here, just like it is. That's just a number, and so what would be the integral or antiderivative? That times x. It's just a number, so that times x would be antiderivative. plus 3/4. Yeah, we're doing the integral, but x minus 4, technically I guess it's u substitution, but du is dx, and so really just going to do the power rule here. Because the du is dx, but confirm that if you want. But that antiderivative is just going to be 3/4 times 1/2 x to the minus 4 squared. And then here, what is that, negative 3/32? Same thing here, because u equals x minus 4. Here's what I'm saying. Du is dx. And so we have u squared du. So there's no extra factor in there, whatever you want to say. Just power rule. 1/3 times that x minus 4 cubed. Those are pretty nice. With me there? Any questions how I got that? And then we'll do 3 to 5 done. Any questions on how I got here? Good with that? Okay. All right, so let's plug in 5. So that'd be ln of 64 times 5. And that's ln of 64 times 5. What's that? 3/8. Oh, 5. Plug in 5 there, you got 1 squared. 3's going to cancel, so that's just going to be 1/32. And then 5 again is 1/3. Just about the same with 3. So we'd have ln of 64 times 3. Plus 3/8. Now you plug in 3, you get negative 1 squared, but that's still 1. And then here you get 1 minus 1/32, negative 1 cubed. There'll be a negative 1 there. But so this integral is approximately whatever that is, which is terribly nice, but it's just a number. All right, so ln of 64 times 5. Plus 3/8 minus 1/32 minus ln of 64 times 3 minus, I don't know, plus 3/8 again in parentheses, and minus, that would be a minus times a minus, so it would be plus 1/3 inside the parentheses. As we distribute the minus, it'll be back to minus. Anyway, all right, 8.255 266,167, and I don't know what. Let's do it this way. I know the 6 is correct there. Little birdie told me here this is the actual value is 8.2540. 8.2540. So pretty good with 3 terms again. Pretty good approximation. So gives you an idea of how we can do these approximations with these Taylor series. All right, got, I was about to say, just one more example. Good with that? That's good. All right, so here's find the Taylor polynomials up to degree 4 for f of x equals negative sine of x centered at a equals pi over 2. And then we'll graph f and these particular polynomials. Taylor polynomials here. Nothing else, just to kind of show you how they group it and organize it here. Since I've got 4 of them, let's kind of arrange this in a table. So I want to do it up to n equal, Taylor polynomials up to degree 4. So that would mean I want to do a Taylor polynomial n equals 0, n equals 1, 2, and 3, and 4. So I've got quite a bit of information here. And I think this is the way they organize it in the book or something like that. So you don't have to do it this way, but so let's just put in this column the nth derivative because I need those my Taylor polynomials. All right. So yeah, that's just f of x, which is negative sine of x. So this would be the derivative of that, which is negative cosine of x. And then this would be the derivative of that, which is positive sine of x, cosine of x, and then the 4th derivative would be negative sine of x. Back around here. Now, in the Taylor polynomials, I need those evaluated at a, which in this case would be pi over 2. These are just doing the derivatives. And then we'll put it all together. It's just kind of organized in a different way. That's important. All right, so the nth derivative evaluate. So this one evaluated at pi over 2. What's sine of pi over 2? 1. So minus 1. Cosine of pi over 2, 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Minus sine of pi over 2 is again back to minus 1. Okay. So now we can do our Taylor polynomials. So this would be T0x right here. T0x is just f evaluated at a, which in this case would be f evaluated at pi over 2, which is, we got it right here, negative 1. So T0 of x is negative 1. T1x, well, that's n equals 0 and n equals 1 terms. It's the partial sum. So we take the negative 1 and add to that our first derivative at a over n factorial times x minus a first. Well, that's what, so in this case, our first derivative at a is 0. So it'll be negative 1 plus 0 over 1 times x minus pi over 2, but that's really of no consequence because that's 0 anyway. I don't know if this is helping. But sometimes that happens. Notice sometimes this happens. T0 and T1 are exactly the same because the first term zeroed out. That can happen. And I guess hence why we say non-zero terms on some of those things. Anyway, all right. So T2x would be n equals 0, n equals 1, and then the n equals 2 term, which would be the second derivative at a, which is 1, over 2 factorial times x minus a, which is pi over 2 squared. So that's just negative 1 plus 1/2 x minus pi over 2 squared. Because that n equals 1 term is 0. What happens at T3x? Well, take that. That's to n equals 2. And then do the n equals 3 term. Well, the derivative, the third derivative is 0 over 3 factorial times x minus pi over 2 cubed. But again, that's zeroing out. And so we're left back with the very same thing we had started with, if you will. And so last but not least, T4x. So T4x would take T3x and add the next term. Which, technically, the next term, we went up to n equals 3 here, so I go to n equals 4 here. N equals 4, we'd have the fourth derivative evaluated at pi over 2, which is, that's why this chart here is negative 1 divided by 4 factorial times x minus pi over 2 to the fourth. And I think, unless we simplify that, negative 1 over 24. Yeah. Yeah, if I go through it here. I don't think it'll be too bad here since a couple of them are the same. All right, so f, of course, we got negative sine of x. We know what that looks like. Let's see, I'm going to look at it. Negative 1 to 5. And it's negative 4 to 4. Window here. Okay, so let's graph. So we got negative sine of x. And the first two are just negative 1, so that's probably not going to. No, I guess it'll do pretty good. And then T2x is negative 1 plus 1/2 x minus pi over 2 squared. Let's see what those are. Kind of swoops in here. Oh yeah. Okay, so sine of x. Kind of that in that view. Negative sine of x, I should say. All right, so T0 and T1 are just y equals negative 1, so yeah, that's not going to match it very well. T2x, all right, so that does a little better because it does real good, like from here to here. Really matches up. Kind of veers off there. So this is T0 and T1 right here. And then last but not least, T4. Negative 1 plus 1/2 x pi over 2 squared minus, that'd be 1 over 24. X minus pi over 2. Fourth. Yeah, I did not do it. What did I do wrong? Oh. Is that better? Yes, okay. T2, T3. Oh, okay. Yeah, so the good thing about T4 here is it starts matching up even out here, these little curvatures. So T4 comes in kind of like this. So it starts matching it even with the sine cycle. You can see kind of what the beginnings of that is what's going to occur there. All right. Now, one other thing they had on this is, do it right here if I can. So it's evaluate f and these at x equals 2 pi over 3, pi, and 4 pi over 3. So just kind of arrange it however you want to, but so f of x, well, f of x is negative sine of x, so at 2 pi over 3 you get negative 0.8660, pi you get 0, and 4 pi over 3 you get positive 0.8660, approximately. Now, T0 and T1 are easy to evaluate at these because they're always -1. So they're not going to match really well. All right, so T2 at those, so if I plug in x to be 2 pi over 3, so 2 pi over 3 minus pi over 2, I get, oh, this is T2 and T3. It just so happens those two are the same, right? Because the third n equals 3 term was 0. Anyway, if you plug those in, you get negative 0.8629. At pi, you get 0.2337. And then at 4 pi over 3, you get 2.4269. And so you can see, yeah, that's a little bit off there. 0.86624. It's kind of close right there. But why is that? Well, 2 pi over 3, I centered this at pi over 2. 2 pi over 3, pi over 2 is 2 pi over 4, so that's pretty close to pi over 2. Pi is getting a little further out, and then 4 pi over 3, that's, I guess pi over 2 would be about 1.5, so it's right up there. 4 pi over 3 is 1 1/3 pi, so you're getting over here in this area, so it makes sense that those are veering off. And then T4 at 2 pi over 3, so if I plug in 2 pi over 3 here, gives me, oh, look at this. Pretty nice match to f of x. At pi, I get negative 0.01997, so it's doing a better job. The real value is 0. That's pretty close to 0. And then this one's 0.4644. So we're getting out here where it's a little bit of a gap. So just again confirming kind of what we see visually on the graph right there. The last thing I was going to mention before let you turn off here is kind of a technicality, but let me just show you this. If I say find T3x for cosine, f of x equals cosine x for a equals 0. It's just kind of a technicality, but I think it might pop up on the homework. Well, T3x will be f of a, then the first term, a prime of a, over 1 factorial x minus a to the first, second derivative at a, over 2 factorial x minus a squared, T3, okay, so one more. Here's what I was going to say. Okay, so I've got 0, so it's f of 0, f prime is 0, is x minus a, f double prime is 0. Oh, and then x minus a is 0, so this would just be x. This would be x squared. This would be third derivative at a, 0, 3 factorial is x cubed. Okay, well, all right, so each one of these, all right, so f of 0, cosine of 0 is 1. F prime is 0, well, f prime is negative sine of x. At 0, that is 0. So that turns 0. And then f double prime, so the second derivative would be negative cosine of x, which is, at 0 would be negative 1 times x squared. And then third derivative at 0, the third derivative of x is positive sine of x. And then at 0 would be 0. Which is going to make that whole term 0. So, technically speaking, T3x is 1 minus 1/2 x squared. That's T3x. Third degree Taylor polynomial. What I was going to show you is, the Maclaurin series doesn't technically give you these Taylor polynomials. Maclaurin series, again, it's n equals 0, infinity, yeah, I remember it, negative 1 to the n, x to the 2n over 2n factorial. Okay. The reason that won't give you the correct Taylor polynomial is because this is kind of weeded out the 0 terms. And when you do the Taylor polynomials, you get some of these 0 terms, especially when you're dealing with sine and cosine of, the quadrantal angles, 0, pi over 2, 2 pi. You're going to get some 0 terms. And this doesn't factor those in. Because if I did to n equals 3 there, I'm going to get 4 terms. So that was the technicality I was going to say. If you're wanting a Taylor polynomial, don't use the Maclaurin series. And so that's why, on that other example, I steered away from Taylor polynomial. It was probably okay because it said non-zero terms. But yeah, Taylor polynomials, sometimes you get those 0 terms.